Right, here's the deal about this linearity of an operator. If you put these two operators like this is not L bracket, this is L parentheses, and M1 and M2 are not functions, these are operators. Just like a D with the integral operator or integral operator with a D. Suppose we have operator done an M plus M2 first, and then we're doing this L operator later. Is there a way to rewrite this operator algebra in a different way? It is the linearity that guarantees this is the same as LM1 plus LM2. If we write things like this, L of M1 plus M2, if these are numbers or if these are functions, usually this is an obvious. There's no condition required to conclude that this is so, like this. But the reason this is a big deal is that this is not a multiplication, this is a composition. And that's why we need a condition to expand this one like this. But here's something that's different. If you have this L, if you do this L operator first and then doing this one later, is by definition, it's just this. This does not require any linearity to conclude. This very definition of M1 plus M2 operator is applying this M1 to the L and M2 to the L and add them together. This is the definition of this operator M1 plus M2. But L cannot be separated like this. It requires this property of a linearity to do this. So there's a big difference in here. Again, although we're using this multiplication notation right here, this is a composition of two operators, and this multiplicative algebra between these linear operators, it behaves just like a number case, as if these are multiplication. Alright, so the way the proof goes is that we want to show this operator is the same as that operator. And two operators are same if they operate on arbitrary function exactly the same way. So this is operator, and we act on some arbitrary function, and we show this is a function, right? This function is equal to this function right here. So we'll go through the definition of this M1 plus M2 and use the linearity to go from here to there. So by definition of inside operator M1 plus M2, we operate M1 to y, M2 y, and add them together. That's the very definition of this M1 plus M2 as an operator. Now inside of this L is a sum of two functions. Here's where linearity is used. So here, since L is linear, you can operate on that, plus L is operating on that. If this part's not linear, if L is not linear, you can't go from here to there. Now if you look at this part, that's exactly the notation LM1 y, LM2 y, so this fits into this notation. So if L is linear, this composition, written as a multiplication notation in the operator algebra, is actually behaving just like a number under the condition of linearity. So we're back to this picture here again. So we have this operator D and integral operator, and we know how they, if we put this together as if it is using the multiplicative notation, then we've learned some of the rules. And when we add them together and then operate on the left or right, we need this linearity to say something for sure. So these are all linear operators, therefore the way that algebraically behaves is as follows. For example, I copied and summarized it here. If L is linear, this looks like just number notation. L is multiplied to LM1 plus LM2. What is this called? It's called distribution law. The distribution law holds for operators if it's a linear operator. And distribution law on the right, it's the obvious one. It does not require linearity. All right? So that's little sensitivity about the algebra of operators written as a multiplicative notation like this. But it's not multiplication. So with this much of the tool, we can kind of analyze or decompose some of the complicated looking operators into a smaller fragmentary operators. For example, we can you can factor some of the complicated operator as a product of simpler operator and stuff like that. So if you think about it, it's a quite amazing thinking. Just like we did it over here, and we factored and manipulated number and prime numbers and stuff like that, and we can do the same for the functions, and we can do same for the operators. As if we have arithmetic down in numbers, we have same sort of arithmetic and slightly more sensitive and complicated, but we can break down complicated things to simpler things like we do factor numbers down to prime numbers and stuff like that.